A lot of test prep programs claim that they will improve student scores, but a retake may improve test scores without the expense of test prep. 8 students took the LSAT twice to see if there was an improvement on the second attempt. Use the results below and a 1% significance level to test the claim. So let's stop there and identify the fact that they're asking us to test a claim, so we know we're dealing with a hypothesis test, to test a claim that there is a difference between the two attempts. What do these results say about the test prep industry? So we want to test the claim that there's a difference between the two attempts. So when I look at the layout of the data, it leads me to believe that this is a dependent t-test. The reason why is because I have, of course, this is the first subject's first score and second score. This is the second subject's first score and second score. So every person in this problem is taking the test twice. So even though there's two sets of data here, the data sets are dependent because these scores are connected by the people who take the exams. For example, this guy obviously has better scores than this guy. So, we expect that those scores, the first and the second score here will generally be lower than this guy's first and second scores, right? But that's not really what we want to know. We don't want to compare the students. We want to compare their before and after type results. So we want to compare their first score to their second score to see if there's a natural improvement just by retaking the exam. So this is a dependent t-test, that's clear. Small sample size, the layout of the data, the fact that the data is dependent, that all indicates it's a small sample t-test and dependent t-test at that. So now from here, once we realize that, we should just go ahead and begin to do the problem working from that point of view. So let's start with the idea that the claim is going to be that there's a difference between the two attempts. So all that's saying is that there's going to be some change, right? It doesn't tell us what kind of change. It just says there's going to be a difference between them. So let's start with the idea that the claim will be the mean for the first attempt is going to be different from the mean for the second attempt, right? Because they say there's a difference. If there wasn't a difference, then we would say they're equal. But they're saying there's a difference, so we're saying that they are not equal. And then from there, that can lead to the idea that if I move this guy over across the not equal sign, I'll end up with the idea that the mean for the first attempt minus the mean for the second attempt is not equal to 0. And then lastly, that of course is the same as saying the average difference is not equal to 0. Okay, so that's my claim. Now once I have my claim, the next step is to identify HO and HA. So for this, we're going to look at the claim and see that the symbol here is not equal to. That means it's the same as HA, right? Because that's one of HA's symbols. And then HO has to be the opposite of that. So it's going to be the mean difference is equal to 0 for HO. Now from there, we're going to basically get the data for the problem. And the data for the problem, remember, consists of summary statistics like N for the differences, and how many differences are there. We're going to have the X bar for the differences, right? And we're going to have the standard deviation for the differences in these problems, and we're going to have an alpha value. Now, when we say N for the differences, X bar for the differences, we're talking about the differences that we will calculate down here, right? So we're going to calculate the differences, and then when we're done, we'll get these summary values. Okay, so let's just do the subtraction first minus second. The reason why I want to do it that way is because you see that's how I did it here. 1 minus 2. So it's important to do the subtraction in that order. If we don't do it in that order, we're going to end up with a different test stat than we should have. Our test stat will basically have the wrong sign and be on the wrong side of our bell curve when we compare it to the critical value. So let's make sure we're consistent with what we did in the claim. All right, so I'm going to do this minus this. Well, 161 minus 165 gives you -4 because the bottom number is bigger, right? The difference between these is 5, but it's -5 again because the bottom value is bigger. The difference between these is 8, but it's -8. The difference between these is 2, it's -2 though, because it's different. These are the same, so we get a 0, right? Then the difference between these two is 5, but it will again be -5 because the bottom number is bigger. This will be -7 because the bottom number is bigger. And then lastly, -4, once again negative because the bottom number is the bigger of them. All right, so how many differences are there? There's 1, 2, 3, 4, 5, 6, 7, 8. So there's our 8 for N sub D. All right, from there we're going to get the other values from my calculator because I've entered all these differences in my calculator already and done some calculations using the calculator software to speed things up. And I find the answer is -4.375, and the standard deviation is 2.5599 dot, 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 right? And then alpha in the problem is 1%. So I'll go ahead and write that as 1% or 0.01. Okay, now from here, let's go ahead and plug this into our test stat formula. Our test stat formula will be a t test statistic, and the formula is going to be x bar for the differences minus the value from HO, so in that case it's going to be 0, divided by S sub d over the square root of n sub d. So for us that's going to be minus 4.375 minus 0 is just that, divided by the standard deviation, which is 2.55999 dot dot dot, all over the square root of 8. Okay, let's plug that stuff into our calculator now and see what we get. Okay, so we're going to start with the top part, minus 4.375 divided by, use parentheses for the bottom, 2.55999, and then, actually I don't remember what came after that, but it's okay, that's enough decimal places to put in the calculator. We shouldn't get a rounding error at that point. And then divided by the square root of 8, close the parenthesis twice, hit enter, and we get the answer minus 4.83, minus 4.83. Okay, so I can tell this is a pretty extreme test statistic. At this point, if I was by myself doing this for my own personal knowledge, I would stop and say that means that we reject the null hypothesis, because I can tell that number is extreme enough that we're going to probably be able to reject the null hypothesis. It's going to fall into the rejection region. But to be sure, I better calculate the critical value or determine what the critical value is and compare it against that. So I'm going to draw a bell curve. And I'm going to label the rejection region based on HA. Because it's not equal to, we're going to have a two-tailed test. Zero in the center, put a T here at the bottom number line here. And then from there, what I want to do is basically go to our table and look up the appropriate T value. So in this case, it'll be a T alpha divided by 2 value, because it's split into two tails. So that's going to be half of the 0.01. That's going to be 0.005, right? Half of 0.01 is 0.005. And then the degrees of freedom is just going to be this guy, the n value minus 1, which will be 7, okay? So we're going to look that up on our chart and figure out what our critical value is. So let's go to the chart, look in the 0.005 column, and look at degrees of freedom 7 to determine the appropriate critical value. Okay, so we're looking at 0.005 with 7 degrees of freedom. The answer is 3.499. Okay, so we found our critical value to be 3.499. 3.499, and of course negative 3.499. Now if our test stat lands in either of the shaded regions, we conclude that we'll reject the null hypothesis. And of course you see that negative 4.83 is in fact on the left here in the shaded region, so we're going to conclude that we should reject HO. And of course if we're going to reject HO, we should support HA. All right, now at that point, we look at our claim and we identify whether it was HO or HA. You can tell by its symbol it was HA, pardon me. So we're going to underline that and say that that's what we should word our final conclusion as. So we're going to say the sample data support the claim. The sample data support the claim. And of course, what was the claim in this problem? The claim was that basically there is a difference between the before and after scores when you take the LSAT twice. So that essentially means that when you take it a second time, you end up with higher scores, it looks like, because when you look at our list of values here, you can see that those values were almost universally higher. There's only one case where it wasn't higher, it was a tie. But in every other case, the people scored a little higher when they took the test again. And so we're saying that that's a statistically significant difference there. We're basically saying that it looks like taking the test twice will improve your score.